Okay, let's get started. Let me put this on. Oh, thank you, Arash. I appreciate it. Thanks a lot. All right, see you. Yeah, I don't need sugar. Okay. Now that I have my fuel, I can go. Right? It's the coffee. We have a smaller crowd today for, I assume, because of the Easter break, right? I see these sides empty. So you guys all are the more motivated ones. And the recording is okay? Okay, perfect. Okay, let's get started then. So since we don't have a lecture tomorrow, I'm going to keep the break short today so that this doesn't come as a surprise for you. But the good news is you're going to enjoy your Easter break starting from tomorrow. Sounds good? We'll make that deal beforehand so that you don't get surprised. Okay, cool. I can see that I have the support of several. That's good. Okay, so we're going to talk about some exciting stuff. Microarchitecture, we're finally transitioning into how to implement the ISA. Last lectures, we talked about the von Neumann model and architecture, ISAs. And hopefully you know by now that instruction set architecture is the interface between the hardware and the software. What the hardware promises and what the software programmer relies on. We're going to talk a little bit more about that actually. And if we have time, we're going to talk about some of the trade-offs to make in that interface. Because we did talk about the interface, but we didn't talk a lot about the trade-offs on how you design that interface. And those trade-offs actually affect a lot of things in the system. But unfortunately, we don't have enough time. So we'll see. We'll cover some of those trade-offs, and if time permits, we're going to go into more of those trade-offs. And looks like this is working. That's good. So these are your readings. Let me try this fancy functionality. No, that's not what I want, though. Use slideshow. Okay. Now it's more fancy. You can see it, right? That's good. So next week, we're going to cover multi-cycle microarchitecture. It's not very good. I should be able to point to it, and it should work right. And microprogramming and pipelining. This week, we're going to cover, basically, we've covered this. And you've already been reading some other readings. So please do the readings. If you have time over the break, I would suggest catching up with the readings. It'll be important. Okay, so this is our agenda going forward in the course. Basically, we've covered ISA, assembly programming. Today, we'll do microarchitecture. Next week, we're going to go in more deep into microarchitecture, basically. We'll talk about multi-cycle microarchitectures, microprogramming, pipelining, out-of-order execution. And there's more to come, which doesn't fit into the slide. But you will get a very good idea of how an existing processor works. And you will see out-of-order execution, which I'm going to talk about briefly today also. Okay, just to jog your memory, we've been talking about the von Neumann model. We're going to assume that for a while. But before I go further in assuming that, I'm going to deconstruct the von Neumann model a little bit, because I don't want you to keep thinking that this is the only model in the world, because things may change a lot going forward also. Okay, this is the von Neumann machine, so hopefully you know exactly how this works, right? You see the control unit, you see the processing unit over here on the right, and memory input-output. And remember the instruction cycle. So we talked about the instruction cycle, and we're going to implement it in a machine using real hardware components today. Okay, so ISA, again, recall, it's the interface between the hardware and the software. What the software commands and what the hardware carries out. It's really a contract between them. So the software expects something to happen, the hardware should really deliver it. Okay, and this is again to jog your memory. Hopefully you remember all of this, right? We'll actually later say that ISA is broader than this. So it's not just the memory, it's not just the registers, it's not just the instruction set. The first part of this lecture will talk about other stuff in the ISA. Because as a software programmer, especially as a systems programmer, you need to know more things about the hardware. Okay, microarchitecture simply is an implementation of an ISA. And I said it's an implementation because there could be many, many implementations. The key question we're going to try to answer today and in the rest of the course actually is how do we implement the ISA? So we will discuss this for many lectures. There can be many, many implementations of the same ISA. MIPS, for example, is the ISA that we looked at. There have been many, many implementations over the years. I don't know what the latest implementation is called, but one of the initial implementations was called R2000. And at that point in time, people said, oh, this is the fastest processor that we're going to ever make. Why do we need faster processors? This is 1980s, late 1980s. And MIPS R10000 is a much, much faster processor that includes a lot of the concepts that I had on the slide earlier, out-of-order execution. MIPS R2000 was a very simple pipeline, very similar to the things that we're going to study soon. So Intel, for example, has many, many implementations. I don't know if there's anybody who's as old here to remember 8486. Does anybody remember what an 8486 is? Let's see. Okay. It's an implementation of the x86 ISA, instruction-set architecture, which is one of the most dominant ISAs today. And this was my first computer. Actually, I had an 8486. Actually, I had an 8386. I should have put that over there, too. But then there have been many, many other implementations, Pentium, Pentium Pro, Pentium 4. Now I think one of the latest ones is Coffee Lake. I cannot keep up with these names, but you can easily figure out. Basically, these are implementations of the same ISA. Now, it's not very fair to say it's exactly the same ISA because the ISA also evolves over time, but it's really fundamentally the same ISA. Okay, so first, let's talk a bit more on the ISA design and trade-offs before we jump into microarchitecture, because I think there are some fundamental concepts we should talk about. And I'll ask you the question, actually, you studied the von Neumann model. It's also called the stored program computer. And we had the reference in the last lecture Juan gave. There are two key properties to the von Neumann model. Can anybody name them? If you name them correctly, you'll get these, but I'm not sure if I recommend eating these because these were here when I arrived. These are little Easter egg chocolates. It'll be up to you to decide whether or not you eat them. Actually, there are 3 of them, but I have only 2 on the slide. So, anybody? What are the 2 key properties of the von Neumann model? Like, these are the really fundamental properties. Of course, it has memory, it has control unit, but they're not as fundamental. Any guesses? How do they instruct? Yes, there you go. Okay. That's not what I was looking for, but that's true for many models, yes. Yes, exactly. That's one. This gave both of them, sorry. No, I cannot ask. Are you able to catch this, you think? Let's see how precise I will be. There you go. Cool. Yeah, so it's up to you whether you will eat it. I don't take any responsibility for what happens after you eat it, if you eat it. Okay, the first property is stored program computer. And if you read the von Neumann chapter, then you would know this answer. So that's a good test. From not this book. Actually, this book maybe covers it also, but I don't think it does. The other book, Kadam Patel. So instructions are stored in a linear memory array, and memory is unified between instructions and data. Basically, the interpretation of a stored data value in memory depends on the control signals. We're going to talk a lot about control signals. You've seen them last lecture a little bit when we talked about instructions and how do you control the execution of an instruction, right? But basically, instructions and data are the same. Whether some piece of value, let's say 4,000, is interpreted as an instruction or data depends on when you're actually accessing that value, which control signals you assert. So basically, the key question is, when is a value interpreted as an instruction? The answer to that should be going back to this slide that I had. Sorry for going back too much, but this slide, essentially. If you're actually accessing that value over here in the fetch stage, if you're accessing memory in the fetch stage, then you're interpreting that value that you get from memory as an instruction. If you're accessing memory in the fetch operand stage, this is not very precise, as you can see. We'll need to figure out how to make it precise. But if you're accessing memory in the fetch operand state, you're also accessing memory, then you're interpreting the data value that you get as a data value. So you assert different control signals during the fetch stage or fetch phase and the fetch operands phase. This is a fetch instruction. To be more precise, this could have been called fetch instruction. Okay, I'll go quickly. So that's the one fundamental issue. But the second, even more fundamental concept that's going to affect a lot of the lectures that we're going to look at in the next is sequential instruction processing. Basically, instructions are processed in a sequence. you process one instruction, fetch, execute, and complete it, go through that instruction cycle before you start the next instruction. At least that's conceptually what's proposed to the programmer, right? You don't fetch the next instruction while you're fetching the current instruction, okay? So basically, everything is controlled by this program counter or instruction pointer. I like the name instruction pointer much more. Basically, instruction pointer points to the address of the instruction, and then that's the current instruction that's being executed. You fetch it, you decode it, you generate the address, you fetch the operands, you execute it, and you store the result. Those are the 6 phases of instruction execution, right? And then you move on to the next instruction. So program counters advance sequentially after that to the next instruction, unless there's a control transfer instruction, as we've seen in the last lectures. So the sequential execution, everything is sequential. And one instruction finishes before the next one starts. Okay, and these are the readings that you can take a look at. Clearly, this reading is very important. Oh, I'm not used to this one. Okay, the von Neumann model chapter, you should definitely read that. Okay, and this was a picture that we looked at. So I'll ask one question. I said I'll deconstruct the von Neumann model a little bit. I'll ask the question, is this the only way that a computer can operate? I'm really asking, is this the only way you design the ISA and expose it to the programmer? I heard a yes. Somebody says no. Okay, I'll take the no. Because there are many, many other ways. As you can imagine, people can think of many other ways. Qualified answer would be no, but it's been the dominant way. That's why a lot of the processors that we have over here, for example, are operating this way, really. We can go into that more. So it has been the dominant paradigm for computing for n decades, where n is a large number. You see that the previous paper was published in 1946, and the concepts were around for a long time. Okay, but let's take a look at a different model, just so that you can do some critical thinking and understand what other models may look like. So let's recap the von Neumann model. In von Neumann model, an instruction is fetched and executed in control flow order, as specified by the instruction pointer. And instruction pointer is incremented sequentially unless there's an explicit control flow instruction. Now let's take a look at a completely different model. I'll call this the data flow model. And I'm going to fetch and execute instructions not in a sequential order. There is no program counter anymore. Ignore it. I'm going to say I'm going to fetch an instruction in the data flow order. What does this mean? When its operands are ready. Meaning somehow I'm going to identify the operands of an instruction are ready to execute, and I'm going to fetch the instruction at that time and execute the instruction and generate the result. And the result will enable some other instruction to execute because it's going to be the operand of some other instruction. Right? That's the idea. So now we've eliminated something that we thought was fundamental to the ISA, right? Instruction pointer. We got rid of it. You don't need an instruction pointer for this. You need an address to fetch from memory from, but that's not an instruction pointer. That's not a program counter anymore. Okay, so basically this is another model. Instruction ordering in this model is specified by the dependence, data flow dependence. Each instruction specifies who or which other instruction should receive the result. So you have an explicit pointer to some other instruction saying this instruction should receive my result. Now, how do you encode it? Those are issues that are left to the ISA designer, which we're not going to go into a lot of detail about. And an instruction can fire, or fire means it needs to be fetched and executed whenever all of its operands are received. For example, if you have an add that has 2 operands, when both of the operands are received from potentially different instructions, you can fire that instruction. Firing means that you can fetch that instruction now and execute it. So you don't need a program counter for this, right? You don't need an instruction pointer. Now, the beauty of this is you can execute potentially many, many instructions at the same time, right? If you think about the von Neumann model, you fetch one instruction, execute it, and then you move on to the next one. It's very sequential. This one, you cannot even think about what's the ordering here, right? The ordering is specified by when the operands are ready. And one operand, the readiness of one operand may enable many, many instructions at the same time, right? So it's inherently more parallel. Now, how do you implement is a totally different question. We're not going to talk about that at this point. But let me give you one example of von Neumann versus data flow. Consider this von Neumann program. You can think of this implementing in some assembly language. Clearly, it's sequential, right? You finish this instruction before you move on to this, and then ... basically it's sequential. It doesn't matter exactly what these do. The meaning is not important, but the dependencies are important here, right? So how would you, what is this? So there are two questions over here. What is the significance of the program order? Well, let's specify it. It's sequential, so you can reason about it nicely, perhaps. You can say that this instruction cannot be executed before all of the previous ones are complete. So maybe you can debug it more easily. And we're not going to go into that, but that's one advantage of the von Neumann model. You know exactly what's executed and what is not executed at any given point in time. So significance is essentially what the programmer can reason about. The programmer can easily say, oh, I know which instruction has executed at this moment in time if you're debugging a program, right? What is the significance of the storage locations? This is maybe a little bit different question, right? Now, if you look at the storage locations, this instruction, this add, puts its result into this location. It could be a register, let's say. And then this multiplication puts its result into W. And then you do V minus W over here to generate X, and V plus W here to generate Y. And then you do X times Y to generate Z. So you always write to a location, register, let's say, or memory, it could be a memory location also, to communicate between instructions, right? What you're doing here is really, you're enabling, the storage locations are enabling communication between instructions. Make sense? So this instruction is generating V, and V is used over here. This instruction is generating W, and W is over here, and you can see that that's true. And then this instruction is generating X, and X is used over here. So these could be values that are never going to be needed in the future. The only thing that you may need is Z. But you dedicate storage locations, registers, to these intermediate values. I will call these intermediate values, V, W, and X, and Y. They're just there for communication, to communicate between different instructions, which means that we could potentially eliminate them, right? Okay, so this is a very different view of the same program. That's the data flow view. Data flow is usually more easily understood with these graphical representations. And this does exactly the same thing. Now, I don't have any storage locations, right? Maybe Z I store at the end somewhere over here. So I need a data flow node for that. But basically, you can see that the instructions are represented, operations are represented by nodes, and the inputs are represented by arcs, as well as the outputs are represented by arcs. So you can see this is the arc that is stored in V over here in the sequential program, right? Now, there are a couple of things over here. This node fires when both of its inputs are ready. And it fires and executes, it generates a result. And its results get communicated somehow to these two other nodes. And these two nodes fire when both of their inputs are ready. Let's take a look at this node over here. This node fires when this input is ready, as well as when this input is ready. It may be at the same time, it may be at different times, depending on the latency of these instructions. But this node fires when both of its inputs are ready and generates a result that is communicated to this node over here. Okay, so that's how it operates, basically. A node fires when inputs are ready. The second thing over here is, as you can see, there's no order between instructions, right? I put these two together. There's no specified order, because order is really determined by the data flow. If B, for example, arrives at this graph much, much earlier, this instruction may complete much earlier than this one. But if it so happens that A arrives much earlier, it could happen. Maybe these are inputs, and somebody presses the keyboard, and that's how you get the inputs, right? I don't know. Then this executes before this one. So the ordering is really determined based on when the operands become available. So a very different way of thinking about programming as well, right? And you should think about that. Okay, I'll ask you the question. Which model is more natural to you as a programmer? You've written some programs. Who says von Neumann or sequential? Who said, yeah? Okay, some people. Who says data flow? This one over here. No one. No one, really? Okay. Well, if you actually were programming with data flow from the very beginning, maybe you would say it would give me a different answer, right? So there are other issues over here. Natural is a very interesting question. So some people find this part natural, actually, if they've dealt with data flow in the past. Okay. Okay, so let me give you a little bit more. Basically, we've just discussed this. In a data flow machine, a program consists of data flow nodes. A data flow node fires, it's fetched and executed when all its inputs are ready, when all its inputs have tokens. So we call the input having tokens when the input is ready. And this is one example ISA, instruction set architecture representation of a multiplication. So you have the opcode, you have the first argument, whether it's ready or not, you have the second argument, whether it's ready or not, and you have the destination of the result, the address of the instruction, and where it resides, essentially. I'm not going to go over this in detail, but you can actually build a complete program using a collection of these nodes. I just showed you multiply, add is very similar, but this over here is a branch, right? Let's take a look at it. So a branch takes a data input and a control input, and it has two outputs, true or false. If the control input specifies a false token, the data input is passed to the false path. So in this case, that's the case. The branch fires when both its inputs are ready, when both its input arcs have tokens. In this case, it fired. Unfortunately, it's missing this false over here. Ignore that. Basically, what happens over here is, because the control input is false, all that the branch node does is it passes this X to the false output. If this was true, it would pass the X to the true output. Now you can actually steer the data to the correct instruction, right? Based on whether the input is false or true. You can implement a conditional. Relational is a comparison that basically generates whether true or false tokens, as you can see over here. If the left input is greater than the right input over here, you generate a true. Otherwise, you generate a false. In this case, this node fires when both of its inputs are ready, and it generates a true token when that happens, right? So barrier synchronization is a more advanced concept. I'm not going to go through that in detail, but as you can see over here, the purpose of this node is to synchronize all of the tokens. What does that mean? That means that it has 3 inputs and 3 outputs, and its function is to pass the input token to the output token only when all of the input tokens arrive at the node. See, in this case, this barrier synchronization node fires when all of the input tokens arrive at the node, and it fires only at that point. So if only 2 of them had arrived, this wouldn't fire. This would wait for the third one. And when all of them arrive, it just passes the input tokens to the output tokens. Now, when could this be useful? When you're doing multi-threaded programming, and all of the threads need to wait until all of them generate their result. Now you can use this over here, right? That's a concept of barrier synchronization, and it could be a data flow node in your ISA. Now, this also gives you how complicated ISA instructions can be, right? You've seen very simple instructions. Later, if you have time, we're going to deconstruct some of those things also, but hopefully this opens your mind a little bit. Okay, let me ask you this question. Normally, I would give you a lot of time, but since you have a lot of time during the Easter break, I'm going to give you less time to answer this question. So, by the way, these could be really nice exam questions and relatively easy if you know the concepts. So take that as a hint, maybe. Basically, what does this program do? This is an example data flow program, and I haven't specified all of the nodes over here. But this is 1, this is n, and you need to make some assumptions on n. I think in this case, n is a non-negative integer. But basically, this is a branch node that we talked about. That's a Boolean input. This is a copy node that we didn't talk about. Basically, it takes n and copies it, essentially. Whenever its input node has a token, it generates 2 outputs that basically passes the same token, same value. And there's something that's over here that's a little bit unconventional. You see a loop construct over here. The output of this node comes here, and then goes over here, and then basically, it merges over here. What this means is that in the next iteration, it's not 1 anymore, but the output should really come from here. So that's an iterative construct. Actually, normally in a real data flow machine, there should be a node over here, but I ignored it over here. Similarly, you have this output coming from this decrement. This is decrement node that basically goes into n. Okay, so now you have everything that you need, maybe. N gets copied, it gets compared to greater than 0, that gets copied again, and a Boolean controls these branches over here. And if both of them are true, as you can see, you take a multiplication. And then you decrement one of the values, the secret value, and then the decremented value gets fed back, and the multiplication gets fed back over here. Anybody figured out what this is? So if you haven't seen it, it may take some time, of course. Yes?
Or is it the right term, faculty?
Factorial, yes. I corrected the... So human brain is amazing, right? If you do this to a computer, I'm not sure if they will figure this out. Yeah, it's a factorial, basically. So what it does is, maybe that's the Turing test, right? You do this to a computer and the computer figures it out, then you know that computers are ready to take over. Okay, maybe not. Anyway, I'm not sure if that's true at the moment. But if you look at this, what's happening here is, let's take a look at this path first. N gets copied. So N is available at the beginning. I should have said that also. These two inputs are available at the beginning. That's what the convention is. One is available, N is available, which means that this copy node fires immediately. It generates results N and N. Now N gets compared to 0 over here. And this N, you cannot do anything with it because this branch node doesn't fire until this Boolean is also available. It's not available yet. So let's take a look at this path. Now you have N over here. N gets compared to 0. That's true. Let's assume that N is a non-negative integer first. Well, let's assume that it's a positive integer so that we can go around the loop. N gets copied. Now you get N, oh, this is true, sorry. This becomes true because N is greater than 0. That's what we're assuming for now. So this is true, this is true. True means this branch passes 1 over here. It doesn't go over here. This is the output. True means this branch passes whatever is here, which is N, right? And this is ground, which means that that value gets killed. You don't need to think about it right now. Now we have N over here, and now we have 1 over here, right? So you have 1 times N as the output of this. That gets fed back over here. So at the end of the first iteration, we have N here, right here. And this is N. As we remember, we copied it, and we decrement N. Well, now it becomes interesting. This is N minus 1 over here. So we're going to do the same thing. Check if N minus 1 is greater than 0. If that's true, that's good. We multiply N, whatever we had over here, now it's N. N times N minus 1. And feed it back over here. And decrement N minus 1, that becomes N minus 2. Right. Now you see what's happening. In the next iteration, this N minus 2, if that's greater than 0, you multiply it with whatever we had over here, which is N times N minus 1. So the multiplication's result is N times N minus 1 times N minus 2. And this becomes N minus 3, dot, dot, dot. So that's factorial. Now when does this end? This ends when N is not greater than 0. Then this becomes false. You get the output over here, which is really the M factorial. And this gets killed, so you don't have any tokens lying around, if you will. Only the output token is lying around. And the output token can be fed back to some other data flow graph that's doing something else with this factorial value, right? You can actually build an entire system with a combination of these data flow graphs. So everything that you do can be a data flow graph in a computer. Okay, so hopefully this is clear. If not, you should take a look at it. But this data flow model actually asks the key question, right? And the key question is, that's an ISA level trade-off, instruction set architecture level trade-off. The key question is, do we need an instruction pointer in the ISA? And the answer is clearly not, right? If you accept this model as your ISA, well, if you don't accept, the answer is yes, if you accept the von Neumann model, right? It's control-driven sequential execution. An instruction is executed when the IP points to it, and we discussed this already. But if you say no, one model is data-driven parallel execution, right? An instruction is executed only when its operand values are available. So there are many trade-offs related to that, which we're not going to cover in this course. We may get to it a little bit later on. But ease of programming. So many of you said, I prefer the sequential model, right? Because you may not have ever programmed in data flow model. Yeah, that could be a good question, right? Ease of compilation, performance, whose job is it to extract parallelism? I said, well, Neumann architecture is inherently sequential, and that's obvious, right? Whereas this other one is inherently parallel. In fact, one of the issues that people have had when they design these data flow machines, people actually put a lot of effort in designing data flow machines in the past. especially in the 1980s, late 1970s, 1980s, all the way into early 2000s, actually. And they figured out it's so parallel that you need to control the parallels. You need to basically have limits into the number of instructions that you can allow in the machine. You need to basically say, oh, I cannot execute all the instructions that are enabled by this model. That's very interesting. So hardware complexity is another issue over here. So I put a lot of question marks over here because it really depends on the design. But one thing that it clearly affects is the programmer. At the high level, programmer now gets exposed to something completely different. The assumptions the programmer needs to make is very, very different, right? Okay. So a similar trade-off can be made at the microarchitecture level. So I said you have the von Neumann model and the data flow model, sequential versus data flow. We made that trade-off earlier. We examined it at the ISA level. But you can make the trade-off at the lower level also. Let's take a look at that. So ISA, as you remember, it specifies how the programmer sees the instructions to be executed. Microarchitecture specifies or implements how the underlying implementation actually executes the instructions. At the ISA level, programmer can see a sequential order or a data flow order. But you can also say, I don't care what's happening at the ISA level. I'm just going to execute instructions in any order at the microarchitecture level. I can do it in data flow order, I can do it in the sequential order, or I can do it in some random order. As long as I obey the semantics that I promised to the programmer, which is the instructions at architecture, I'll be fine. That's the idea. That's the beauty of microarchitecture. You can do anything underneath. The ISA can say you're von Neumann. You need to execute instructions sequentially. The hardware designer can say, no, I'm not going to do that because that's very low performance. I'm going to execute instructions in parallel, like in the data flow order. But when I'm going to report the results back to the programmer, I'm going to report them as the ISA specifies it, in program order. So that's the key over here. That way you can actually make a lot of trade-offs at the lower level without making the programmer go crazy, right? So that's the idea. Basically, a lot of microarchitectures today operate that way. Programmer sees a sequential control flow execution order, but underneath the microarchitecture executes instructions out of order in a model very similar to what we've discussed, the data flow execution order. The programmer doesn't specify things with data flow. They specify things as you will specify in your MIPS programs, but the underlying microarchitecture does something completely different. And we're going to talk about that when we get to out-of-order execution in a little bit. But if you want to know about, so we'll get back to the von Neumann model and talk about how to implement it, building our way to that out-of-order execution of instructions. But if you really want to learn more about data flow, this is a seminal paper that introduced the idea in 1974. And people have implemented many data flow computers. This is one of the more accessible papers, even though it may still not be very accessible at this point in time. But you can take a look at it. And if you're really impatient, you can watch a past lecture of mine that's on YouTube. That's linked over here. Okay, so we'll talk about the von Neumann model, as I said, and we're going to implement it now. So all major instruction set architectures today use this model. I'm sure these are some of the major ones. Some of them are dead, unfortunately. Alpha is one of the really nice, clean ones that I've worked on also. But underneath, the execution model of almost all implementations is very different. So the microarchitectures are very different, but the von Neumann model is there. So for example, we will talk about pipelined instruction execution. This was introduced in Intel 8486. I'm looking at the Intel line over here. Multiple instructions at a time. So clearly, pipeline instruction execution, even if you pipeline the instruction execution, what does that mean? You start the execution of the next instruction. You start the fetch of the next instruction while you're decoding the previous instruction. So you're really pipelining the execution of instructions. That also is against the von Neumann model, right? Remember, von Neumann model says you cannot execute an instruction, you cannot start another instruction before you finish the previous one. So that's going to violate the ISA, but we're not going to make the results available to the programmer. Multiple instructions at a time, that's against the von Neumann model also, but we do it in microarchitectures today. Out-of-order execution, initially with Pentium Pro. Actually, Motorola had processors that are before that, but they weren't successful in the market. Even separate instructions and data caches, or separate instruction and data memories, even that is against the von Neumann model at heart, right? Because these are not supposed to be separate, so you need to actually do something to keep them correct. So basically, the key point is, what happens underneath at the implementation that is not consistent with the model should not be exposed to the software. That's the key thing that we're going to do, that we're going to obey. Now today, as we've discussed, now go back to the first lecture, we discussed Meltdown and Spectre, right? That's a very, very interesting discussion because those are side channels. Underneath, microarchitecture does something, speculative execution, which we will see, populates the caches. It really doesn't expose the result to the software, but some people have figured out that, oh, you could get those results somehow. Now the key question that's in the design of microprocessors is, what does it mean exactly to expose the results to the software? So we'll talk about that. So that's the difference between ISA and microarchitecture. Let me define them a little bit more, basically. We're going to talk about some definitions, but let's start with the second one over here. This was done by Amdahl in 1964. Basically, this is the ISA-only definition of architecture. The term architecture is used here to describe the attributes of a system as seen by the programmer. That's essentially ISA, i.e. the conceptual structure and functional behavior, as distinct from the organization of the data flow and the controls, the logic design, and the physical implementation. So today, people think about computer architecture as ISA plus implementation. So it's really the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets some requirements. Requirements can be many, as we will see. Okay, so one more slide on ISA versus microarchitecture, then we'll have some more fun on this topic. Basically, ISA is the agreed-upon interface between the software and the hardware, as we've said. Microarchitecture is a specific implementation, not visible to the software. At least ideally, it should not be visible to the software. Microprocessor, what's the term of the microprocessor? It really consists of all of them, ISA, microarchitecture, plus circuits. So if you hear the term architecture, traditionally it's been used to talk about ISA, but today things have changed, evolved. Today, when people talk about architecture, it's really all of it. So I'm going to distinguish between ISA and microarchitecture when we talk. So let's do this. Oh, that's why. Okay, that's not good. I have an animation error. We'll get back to that why. Okay, so the way I like thinking about it, this actually exists in many, many domains. For example, I have an interface to this, right? This thing has an interface, which is different from the ISA of this one. These two things have different interfaces. But maybe these are not very well standardized. That's why I'm having a lot of trouble right now dealing with them. Yeah, underlying implementation, underlying microarchitectures of these are also very different, right? This thing implements, these two may have had the same interface, but they may have had a very different underlying implementation. I like the example of cars. A lot of the cars have a very similar interface, right? The gas pedal is an interface. That's the interface for the acceleration, right? But internally, engine implements acceleration in some way. And that's true. That's different if you're actually driving a Volkswagen versus, I don't know, a Ford, right? Internally, it's completely different. It's hidden from the user. So that's the difference between ISA and microarchitecture. Another example, add instruction versus adder implementation, right? The MIPS architecture specifies an add instruction that you've seen before. Add register 1 to register 2, store the results in register 3. That's the interface. Underlying implementation can be many. And if you look at chapter 5.2.1 in this book, it talks about several different implementations. Bit serial, carry, ripple carry, carry look ahead. Actually, we've seen the ripple carry adder before, right? We didn't see the carry look ahead, but these all have different trade-offs. Bit serial adder adds a bit in a given cycle. So if you want to do a 32-bit addition, it takes 32 cycles. Carry look ahead, a ripple carry adder adds multiple bits concurrently, but then you need to ripple the carry. And carry look ahead is actually much more aggressive. But then bit serial adder has a high latency but low area. Carry look ahead adder has low latency but very high area, probably a high power consumption also. So that's the trade-off you're making. So underlying implementation still does the add. The programmer expects the add, but the trade-offs are very different. Okay, we've said this already. So microarchitecture usually changes faster than the ISA. There are few ISAs in the world, and some of them are dying, some of them are dead even over here. Alpha is kind of dead. x86 and ARM are more dominant today. But there are many, many microarchitectures. As we can see, x86 over the years had many, many microarchitectures. Can anybody guess why? Okay, well.
Application-specific optimizations.
Mm-hmm.
Like i386 is server.
Mm-hmm. Okay. So you're saying why we have more microarchitectures? Yeah. Okay, that could be one reason. Basically, you can change the microarchitecture without changing the ISA, right? So when you say application-specific, you basically improve the performance of an application without the application changing. Okay, yeah, so that's certainly one of the possible reasons. I agree. Any other reasons? Yes.
I guess once you have written software for an ISA, you don't want to rewrite it every couple of years. But
Exactly.
it turns out you can, well, make more efficient microarchitectures for the same ISA.
Exactly, yeah. So that's the reason why ISA doesn't change as fast. Maybe I should have asked this question the other way around, basically. Why doesn't ISA change as fast as microarchitecture? It's because, not there, it's because of this huge stack, right? If you change the ISA significantly, then it takes a long time for the applications to adapt to it because people need to actually write programs to the new interface. But if you're changing the microarchitecture, you're not changing the interface. And you can do many, many optimizations that could help many, many applications. And the applications are agnostic. You don't need to change the application. So the main reason is you have a huge software that's written for ISA. So for example, x86 is a really good example. There's a lot of software out there that's written for x86. Now, if today Intel says, I'm not going to support x86 anymore, everybody write your code with this new ISA that I've invented. What will happen to Intel, you think? Not so good things, probably. Yes? Well, high-level language gets translated into the ISA at some point. So there's another issue over there, a similar issue actually, right? This is really what we're getting at is the issue of legacy code, right? Or backward compatibility as well, right? If you already have a huge software base and if you change something that requires people to rewrite the software, that's a lot more effort for everybody in the world. Whereas if you can change the microarchitecture without anybody knowing, that's easy, right? It doesn't affect anyone in the world. So that's why ISAs don't change as fast. And that's why ISAs need to be kept compatible with the past. So for example, Intel ISA has evolved from 1970s. And they have these instructions in there, many, many instructions, binary coded decimal, for example. Not many people use that. Some people use that. But there are instructions that operate on binary coded decimal data types. Most people don't use them. Intel can say, I'm going to get rid of it. They cannot say it easily because they don't know exactly how many people use it, right? So there's a lot of software out there that may be using it. So you need to be backward compatible if you want to keep supporting the old software. Backward compatible means compatible with the previous versions of your ISA. So changing the ISA actually has a lot of implications on the software, and that's the major reason over here. In fact, Intel tried to change the ISA completely when they tried to move from the 32-bit ISA to 64-bit ISA. Does anybody know about Intel IA64? Yes, you know about it. Does anybody else know about IA64? So this was Intel's proposal to go from 32 bits to 64 bits. And it was a very, very nice, aggressive proposal, actually, no question about that. And it changed a lot of things in the ISA, but it was not adopted generally. It was adopted by a very small market segment. It was not adopted generally because that required everyone to rewrite their code to execute on the IA64 ISA. Now, what was more successful was at the time AMD's proposal. So today's x86-64 ISA is actually AMD's proposal. The proposal was do minimal changes to the x86-64 ISA such that you can accommodate 64-bit data types. So if you do minimal changes, if you keep backward compatibility, it's easier to keep the higher level software. Now this may portray a negative picture. So how does innovation come about? Well, you need to have a really good idea to change the ISA, basically. That's what I'm pointing to. Okay, let me continue a little bit, and then we'll take a short break. As I said, we're way slower than I expected. Okay, so this is ISA. Basically, it's really the specification in this manual. I'm not going to go over this, but this is just to say that there are many, many other things in an ISA that the software programmer needs to know, like access control, priority, privilege, all these security issues, task management, power management, thermal management. We haven't discussed any of this, but this is just to keep your mind open. This book is the specification of the ISA, at least this ISA over here, as you can see. It's not just the instructions, but we're going to focus a lot on the instructions because we need to focus on the basics for now. Okay, and we've discussed microarchitecture. It's the implementation of the ISA under specific design constraints and goals. And there are many, many things that are possible here. I'm not going to go over this in detail. But let's do this fun exercise before we take a break. Basically, property of ISA versus microarchitecture. I'll ask you the question. Add instructions opcode. Is that a property of an ISA or microarchitecture? Who says ISA? Okay, who says microarchitecture? Okay, no one, that's good. Who abstains? Okay, some people abstain. It's really ISA, right? Because add instructions opcode gets exposed to the, so the key litmus test is, does it get exposed to the programmer or some programmer? It does. How you build the multiplier? You don't need to know exactly what these multipliers are, but there are different types, Booth multiplier or Wall Street multiplier. In the end, they do a multiplication. This is a property of the microarchitecture, right? It doesn't tell anything about the interface that's exposed to the programmer. Now, if you choose to expose the type of the multiplier to the programmer and ask the programmer to know about this, then that becomes a property of the ISA, but that's probably not a good idea. Number of general purpose registers, ISA or microarchitecture? Who says ISA? Okay, who says microarchitecture? Okay, wow, that's... Okay, so let's look at the interface. If you look at MIPS, it clearly specifies that you have 32 registers, right? So that's part of the that's part of the ISA actually, because the programmer needs to know, some programmer needs to know how many registers you have. Now, how you implement those registers, how you implement those instructions is part of microarchitecture. So number of cycles to execute the multiply instruction. This is part of microarchitecture because this doesn't normally get specified in the ISA. Okay? You could potentially specify it in the ISA and tell the programmer, you got to know this because you need to know this to execute the programs correctly, to write the programs correctly. And people have done that in the past. It didn't go too well. You don't want the programmer to know exactly how many cycles it takes to execute an instruction. Okay, number of ports to the register file. How many ports do you have to the register file? Remember, we talked about ports to memory. Is this part of the ISA or microarchitecture? Any guesses? Who says ISA? Okay, nobody. Microarchitecture? Okay, good. Now you got the hang of it, I think. So this is really microarchitecture. This doesn't get exposed to the programmer. Now, number of operands to an instruction, that's a completely different thing, and that's part of the ISA, right? Whether or not the machine employs pipeline instruction execution. ISA? Microarchitecture? Okay, I think most of you got the hang of this. Now again, anything can be exposed to the programmer. It's really, in the end, the definition is, what does the ISA designer decided to expose the programmer to? So basically it's this book. Anyway, I cannot do this. Okay. Okay. So let me do a few more slides and then we'll take a 5-minute break. So essentially, we're making these trade-offs, right? Microarchitecture is a specific implementation of the ISA under specific design constraints and goals. And I think we need to be careful about the design constraints. How do you implement the microarchitecture is very much dictated by the design point. And design point is a set of design considerations and their importance. This leads to trade-offs in both the ISA and the microarchitecture. Let's take a look at some example considerations. Well, there are many actually, so we're not going to take a look at all of them. Cost, performance, maximum power consumption, thermals, energy consumption, battery life, availability, reliability, there's security, safety, predictability. There are many, many of these, right? And clearly, how you implement your adder, for example, has effect on these design constraints. So do you implement a bit serial adder, or do you implement a carry lookahead adder? Do you have a low latency but high power, high area consumption adder? Or do you have a high latency but low power adder? That really depends on the trade-off that you make over here in your design point, right? Cost, performance, power consumption, energy consumption. That's the soul of my trade-offs, right? It's really determined by the design point, which is in turn determined by the problem space, or your intended users, or the market of the computing platform that you're designing. And there are many, I mean, as you can see, there's a huge problem space. I'm not going to go over this, but you can look at the reference. From all the way from scientific applications to transactional, business, network, real-time applications, and there is even more over here. So if you're designing a very general purpose system, you have a problem, right? How do you cater to all of these different markets at the same time? And that's essentially the general purpose vendor's problem. So this may not be as general purpose, but this is also becoming relatively general purpose. It's doing a lot of stuff, right? It may be analyzing my genome at some point. I don't know. But this is clearly more general purpose. People are running many, many things over here. And if you're designing a chip that's used for many, many things, then you have a problem. You need to cater to all of these different applications. Now, if you're being application specific, you can do trade-offs much more easily, right? Clearly, you can, for example, you're designing a specific accelerator for genome analysis. If you do that now, you know your application really well, and you can customize your ISA as well as your microarchitecture much better. But clearly, we have increasingly demanding applications, and this is a slide from a previous lecture. So basically, why am I telling you this? We're going to talk about a lot of trade-offs. We've talked about some of them. Data flow versus von Neumann is one of them. You can make these trade-offs at all levels. You can make the trade-offs at the ISA level. We may talk about that a little bit later on. For example, are your instructions very simple? Add, multiply, XOR, not? Or can they be complex, like a barrier synchronization? Or can you do a string copy in your instruction? Why shouldn't that be an instruction, right? The instructions that we're going to look at, MIPS instructions, are very simple instructions. But that's not the only way of designing an ISA. You can have an instruction that does quicksort, right? You know about quicksort? It's a sorting algorithm, yes. That could be the instruction. The input to the instruction, the parameters could be the beginning pointer to the memory location that's the beginning of the array, and pointer to the memory location that's at the end of the array, and the size of the elements of the array. That's the interface, and the programmer expects the hardware to do quicksort. Right? That's certainly possible. That's an instruction. So the instruction can be complex or simple. That's a trade-off. And clearly the MIPS designers, MIPS ISA designers, or LC3B ISA designers said our instructions are going to be simple. But this clearly has an effect on a lot of things, which we're not going to talk about since we're already running relatively slow. So we're going to talk more about microarchitecture level trade-offs. But I will also, I'd also like to know that there are system and task level trade-offs as well. And these mainly are about how to divide the labor between the hardware and the software. Let's get back to that later on. Basically, computer architecture is really the science and art of making the appropriate design trade-offs to meet a design point. So I'll ask the question, why art? Because I say art over here. I may be criticized for saying it, but it's really an art also. Because we don't know. We don't know the future, right? We're really designing a computing platform. That's today. That computing platform gets used maybe 30 years later, right? I'm using this computer, I think probably for 5 years. Somebody corrected me that I cannot be using it for 5 years because it's a new version. Maybe that's true. I'm using this for 2 or 3 years, definitely. And things are changing, right? So basically, we do not know. And we're designing stuff for things that are going to be used well into the future, right? So there are new demands, new problems, new algorithms that are running on these things. There are new issues and capabilities that are happening at the bottom. Things are changing, basically. People are changing. Like, we have all these social networks today that are very different. The way people use these devices change. And future is also not constant. It also changes, right? And I already said this. I'll give you an analog from microarchitecture, and after that, we will stop for 5 minutes. Remember the 5 minutes. So future, this is actually why it's art. So if you think about architecture, if you talk to architects, architects will tell you that it's all about creativity and art. There's also a lot of science behind it, but creativity and art is very important because there are a lot of similarities to what we have. Future is not constant in macroarchitecture either, right? I'll give an example, that's Juan's favorite example over here. Can a mill later be used as a theater plus restaurant plus conference room? And you may have seen it. Has anybody gone there? This is Mühle, Tief and Brunnen, apparently. Juan's favorite place. It was apparently originally built as a brewery, but to his dismay, it was turned into a mill, and nowadays it's something totally different, right? So clearly people designed it with this in mind, but it's now being used as something else. Clearly things are evolving, right? They're changing things. And that's true for computers also, but maybe we're not as flexible in the computers, right? If you look at this, this doesn't change as much. How do we make it more flexible is a good question to ask. I'll give you another example. Does anybody know where this is? It's also in Zurich. Okay, that's one example. That's the internals. And as you can see, that these people were pretty creative, right? They have actually these shipping containers that the ships use, and they're turned into conference rooms. That's pretty cool, actually. That's another example picture, and you can see this guy being happy inside the conference room. And this is the outside view of the same place. This was an electricity station on Salnaustrasse. Now it's a coffee shop and place for creativity and place where you can actually have meetings. So this is basically my point is things change and you need to adapt to changes. So if you design a very good architecture and microarchitecture, you can adapt to those changes really well for a long time. And also, I mean, if this place was not able to adapt to those changes, maybe it would have been destroyed, right? That's another possibility. Now, it's in general not a good idea to destroy these really nice historical places. But anyway, okay, so let's take a break here for 5 minutes, and then we'll continue with implementing the microarchitecture. Okay, let's get started. Now your fellow students bought you some more time. That's good, by asking questions. But you'll have a lot more time tomorrow. Now let's talk about implementing the ISA. We're going to talk about microarchitecture, and we're going to start with the basics. But now that we have an ISA, the key question is how do we implement it? Basically, how do we design a system that obeys the hardware-software interface? Now I'm going to deconstruct things a little bit because I want you to think critically all the time. This is the hardware-software interface, the ISA. But remember, in lecture 2, we discussed the transmeta experiment. So what your ISA can be translated into something else, right? That's the translation of the ISA. And remember, if you don't remember, go back to lecture 2 where I discussed Transmeta was this bold company that tried to compete with Intel and AMD. They took the x86 ISA and they wrote a software translation layer that translated that x86 ISA to an internal ISA that's a bit different. We'll talk about it, it's VLIW. And then they implemented that ISA. So what is that thing in between? Is that ISA? Is that microarchitecture? It's really a translation layer, right? I call the high-level ISA a virtual ISA, that's x86. That gets translated somehow into an implementation ISA that's hidden from the programmer. So now you have a different interface. What the interface the programmer sees is virtual. What the hardware implements is the implementation ISA. And there's someone's job is to translate the virtual ISA to the implementation ISA. So you can actually affect the trade-offs very, very differently if you do things like this. And Transmeta did this in software. We will talk later that a lot of existing microarchitectures that implement x86 do something very, very similar in hardware. They take the x86 ISA, they translate it in hardware to something that has very simple operations, and then they execute that. We're not going to talk about that at the moment, but keep this in mind. So we will assume hardware, basically, we will assume that we do all of the implementation in hardware. We're going to ignore the translation for now, for most lectures. So we're going to process the instruction. Basically, what does processing an instruction mean? It basically means that you take an beginning architectural state, the program visible state, before the instruction is processed. You process the instruction, and you generate an architectural state prime. Basically, processing an instruction means transforming architectural state to architectural state prime according to the ISA specification of the instruction. And remember the von Neumann model, that's what we're going to assume. And the process instructions step is done this way. Basically, ISA specifies abstractly what the architectural state prime should be given an instruction and architectural state. It's essentially a state machine, right? It defines an abstract finite state machine where state is a programmable visible state, and the next state logic is the instruction execution specification. So you can think of the ISA as an abstract state machine. From the ISA point of view, there are no intermediate states between architectural state and architectural state prime during instruction execution. And that's the von Neumann model, again. There's one state transition per instruction. You go from architectural state to architectural state prime. And what you do in between, there are no states that are visible to the programmer. Microarchitecture, on the other hand, implements how AS is transformed to AS prime. There are many choices, as we've discussed. So we can have many, many programmer invisible states to optimize the speed of instruction execution. This means that you have multiple state transitions per instruction. So one choice, which we're going to call the single cycle machine, is this. You transform the architectural state to architectural state prime in a single clock cycle. Now we're going to see the downsides of this later on also. So that's the simple choice that we're going to examine in this lecture, hopefully. The second choice is what we will call a multi-cycle machine. You transform architectural state to architectural state plus microarchitectural state 1, plus some other intermediate state, plus some other intermediate state. Now, as you can see, we don't change the architectural state while we're transforming over multiple clock cycles. And at the end, we generate architectural state prime. So you take multiple clock cycles to transform AS to AS prime. This is a multi-cycle machine. So the very basic processing engine that we're going to discuss is a single cycle. It takes single clock cycle to execute an instruction. It uses only combinational logic to implement the instruction execution, for the instruction processing step. No intermediate programmable invisible state updates. Basically, this is what we're going to do. Process instruction in one clock cycle. So it's going to look like this, essentially. It has the sequential logic, which stores the architectural state. It has the combinational logic that implements instruction execution. Depending on what the instruction is, it's going to exercise different parts of the combinational logic, and it's going to produce architectural state prime. Okay, we'll talk about this later on. What is the clock cycle time determined by? Clearly, it's going to be determined by the maximum combinational logic delay, right, over here. What is that going to be determined by? It's going to be determined by the slowest instruction to process. So just a foreshadow. Okay. So recall, what is this architectural state? Architectural state is whatever is visible to the programmer. It's the memory, it's the registers, it's the program counter, right? At least in the von Neumann architecture. In data flow, this program counter goes away. Registers may or may not go away also, but we're not going to talk about that. Okay. So, as I said, in a single cycle machine, each instruction takes a single clock cycle. All state updates are made at the end of that clock cycle. So there's a big disadvantage, as we will see later on, but we're still going to cover this. The slowest instruction determines the cycle time. So you have a long clock cycle time. So if one instruction takes, I don't know, 1 million nanoseconds, versus another instruction takes 1 nanosecond, your clock cycle is determined by that instruction that takes 1 million nanoseconds. Probably not a good idea. That's why you don't see single cycle machines around today. You see multi-cycle machines, you see pipeline machines, ... But single cycle machines are a good way of understanding how to implement a data path. On the other hand, in multi-cycle machines, instruction processing is broken into multiple cycles or stages. Then state updates can be made during an instruction's execution, but those state updates are to the microarchitectural state, not to the architectural state. We're not going to touch the memory, we're not going to touch the registers, at least the things that are visible to the programmer. And architectural state updates are made only at the end of an instruction's execution. The advantage over a single cycle is the slowest stage determines the cycle time now. Now, one of your instructions can take 1 million nanoseconds, and another instruction, most of your instructions take 1 nanosecond. So you set your clock cycle time to be 1 nanosecond. So most of your instructions take 1 clock cycle, and this poor instruction takes 1 million clock cycles, right? That's the beauty of a multi-cycle machine, clearly. But both single-cycle and multi-cycle machines literally follow the von Neumann model at the microarchitecture level, as we will see. Okay, we've already talked about this. It's just to make you remember that there's an instruction processing cycle. Don't confuse this with a clock cycle, machine clock cycle. This is also called a processing cycle because you basically do this loop, right? So it consists of 6 steps, as we discussed, steps or stages. Yeah. Okay, instruction processing cycle versus machine clock cycle. In a single cycle machine, all 6 phases of the instruction processing cycle take a single machine clock cycle. In a multi-cycle machine, all 6 phases of the instruction processing cycle can take multiple machine cycles. So it's obvious, hopefully. In fact, each phase itself can take many, many machine cycles to complete. The fetch can be, I don't know, 100 cycles. It could be non-deterministic. It could depend on where the data is. Okay, let's view instruction processing in a different way. Basically, instructions transform data to data prime, or architectural state to architectural state prime. This transformation is done by functional units. Functional unit is a unit that operates on data. We discussed the ALU, arithmetic logic unit. An adder is part of an ALU. We'll see more of that. So these units need to be told what to do with the data. So you need a control unit, essentially. As a result, an instruction processing engine has to consist of 2 different components. One is called the data path. Data path consists of all of the hardware elements that deal with and transform the data signals. These consist of functional units that operate on the data, hardware structures like wires and muxes that enable the flow of data into the functional units and the registers, and storage units that store data like registers. So data path consists of all of these components. They deal with the data. Control logic basically tells the data path what to do. It consists of the hardware elements that determine the control signals, signals that specify what the data path elements should do to the data. So hopefully it's obvious, but this control versus data separation is important because we're going to design these things separately. They're going to interact with each other clearly, but we're going to design them separately. Okay, so think about this. In a single cycle machine, control signals are generated in the same clock cycle as the one during which the data path elements operate on the data, which means that everything related to an instruction happens in one clock cycle. So if you need a control signal to operate on the data, you got to generate it in the same clock cycle. This actually increases your clock cycle time. That's one of the other reasons why single cycle machines are not good. On the other hand, multi-cycle machine gives you a lot more flexibility. What you can do is you can generate the control signals that you need in the next cycle in the current cycle. So you can basically pipeline the generation of the control signals. Essentially, you can overlap the latency of this control signal generation with the latency of data path operation. So you don't wait in a single clock cycle. You generate the control signals earlier. And this is going to be very, very important for the next lectures when we talk about multi-cycle machines. Okay, we will see the difference even more clearly. Okay, there are many ways of designing the data path and control logic, which we will do later in this lecture. It could be single cycle, multi-cycle pipelines. It could be single bus versus multi-bus. In fact, right in the break, one of your colleagues asked me the question, we saw only a single bus data path. Is that the only way of designing it? No, that's not the only way. That was a simple conceptual way in the LC3. You could actually have many, many connections, but single bus is kind of nice and it minimizes the cost, potentially. Hardwired control versus micro-coded, micro-program control. This will be more interesting when we get to it. And the key difference is, do the control signals get generated by combinational logic, or do they get generated by sequential logic? Do you store them in a control structure and get them, fetch them, or do you generate them in hardwired combinational logic? And control signals and structure depend on the data path design, and we will see that actually. So before we move on to an example, let's talk about performance analysis a little bit, because it's going to be important. And I'm going to focus on performance, execution time of a program. There are many, many metrics, as we've seen earlier. Energy is different, power is different, security is something completely different. But let's focus on performance. So performance, we'll define the execution time of an instruction as this. It's cycles per instruction. How many cycles does it take to execute the instruction times the clock cycle time? So let's assume your clock cycle time is 10 nanoseconds. Is that 10 gigahertz? No, it's not 10 gigahertz. 1 nanosecond is 1 gigahertz, right? Okay, 1 nanosecond. And you take 5 clock cycles to execute an add. Essentially, execution time of that instruction is 5 nanoseconds in that case, right? It's simple. Now, if execution time of a program is the sum of execution time of all instructions in the program, clearly, all instructions that you've executed. CPI, basically sum over all instructions, CPI times clock cycle time. There's another way of thinking about it, which is this. Number of instructions times average cycles per instruction across all instructions times the clock cycle time. Now, this is called the performance law of computer architecture or computer design. Now, there are interesting things over here. So clearly, you can improve the performance by reducing the clock cycle time, reducing the cycles it takes to execute an instruction, or reducing the number of instructions you have in a program, right? If you can do all of them at the same time, that's great. And it turns out you have trade-offs in these things. Whenever you try to reduce the clock cycle time, usually you increase the cycles it takes to execute an instruction. Whenever you try to reduce the number of instructions, you make the instructions more complex. Remember the quicksort? Usually you increase either of these, or maybe both of those. Now, it becomes an art and a science at the same time. How do you get the highest performance? By making this multi-dimensional trade-off, right? So ISA design clearly affects this. ISA design implicitly also affects this. Microarchitecture design affects both of these. It cannot affect the number of instructions, right? Microarchitecture is already given the instructions. It can do stuff to those instructions to execute them fast. Fast meaning cycles per instruction and clock cycle time minimize both, but it cannot change the number of instructions. Whereas ISA design affects all of them, although this one it has an indirect effect on. Okay, so single cycle microarchitecture performance. Let's apply this equation to the single cycle microarchitecture performance and multi-cycle. In single cycle, it's easy. Every instruction takes a single cycle, so your CPI is 1, and your clock cycle time is long, because you're really bound by the longest instruction. Multi-cycle, we will see later, CPI is different for each instruction, and average CPI, you can design the microarchitecture such that average CPI is hopefully small. And clock cycle time, you can again design the system such that it's hopefully short. So now we have more flexibility, as you can see. In a single cycle microarchitecture, you don't have a degree of freedom. This is disabled. As a result, this is also crippled. Whereas here, you have 2 degrees of freedom to optimize. You can change the CPI for an instruction, and you can change the clock cycle time across all instructions. Okay, so let's take a closer look at the single cycle microarchitecture that you're going to deal with and love during your labs. Okay, this is a single cycle machine, remember. We're going to start with the state elements, architectural state elements. And as you can see, I'm going to use a slightly different version from this book. You can read this book. The key is going to be, they're going to be very similar. So the single cycle machines that you design are going to be very similar across books. These are going to be from some other book. Actually, these are going to be from the book that is written by the Turing Award winners of this year. It's Patterson and Hennessy. They won the Turing Award for their contributions to computer architecture, for many different contributions that they made over years. But hopefully you will see that the concepts are very fundamental. So we're going to start with this data path elements, right? So this is a program counter. There's a clock over here, input, output. These are the registers, register file. So we have 2 input ports, 2 read input ports, 1 write input port. These are the IDs, and these are the read output ports. This is the write data that you're writing, 32 bits over here, and the register write signal, control signal. Control signals are in orange here. This is the instruction memory. We're going to separate instruction memory and data memory because data memory is writable. And we're going to assume that these are the control signals to the data memory. You can write. When memWrite is asserted, data memory takes write data and writes it to the location that's specified by the address. When memRead is asserted, the data memory takes the address, reads the data, and provides the data. So hopefully these are very simple. Similar things happen over here, except you need to assert explicitly memRead over here to read the memory. Here you don't need to assert explicitly. You're reading. Whenever you provide an instruction address, you're always reading. It's combinational. You can think of this as a combinational state element in a sense. You're always reading from memory. Okay, this is from this book. So just to give you the example similarity, basically I copied it and pasted it from the book. As you can see, you have the program counter, instruction memory, register file, data memory. It's very, very similar. Maybe this doesn't have the read enable signal over here. That's okay. You can make that jump easily. Okay, so for now, we'll assume some magic memory and register file. We'll assume a combinational read. Output of the read data port is a combinational function of the register file contents and the corresponding read select port, and synchronous write. Basically, the selected register is updated at the positive edge of the clock cycle, clock transition. Of course, when the write enable is asserted. When the write enable is not asserted, you're not updating anything. So you cannot affect read output in between clock edges, as we discussed earlier, right? This is important. And we are going to assume single cycle synchronous memory. We're going to deconstruct that later. So basically, what does this mean? You access memory in a single cycle. That's it. And actually part of a single cycle, not even the entire cycle. You can contrast this with a more asynchronous memory that tells you when it's ready, when the data is ready. You can give the address to the memory, write the address to the MAR, memory address register, and wait. And the memory sets a signal, ready signal, only after it's ready to respond. And we will talk about that when we talk about multi-cycle machines. You do need something like this for multi-cycle machines. Memory is not a single cycle in that case. Here we're going to assume that memory is going to consume only a part of the cycle. And that's one of the reasons why this model is not very realistic, actually, right? Because if your memory takes 1 million nanoseconds, why do you want your cycle time to be the same as 1 million nanoseconds, plus some change? Okay, so we're going to look at instruction processing. There are 5 generic steps, very similar to the 6 phases. So we're going to put these components together, right? This is program counter. Instruction fetch will take the program counter, access instruction memory. Instruction decode will decode the instruction, generate the control signals, and access the registers. Execute and evaluate memory address. We'll use the ALU with the input registers and immediates to generate an address or to generate a result from the ALU. And if this is a memory instruction, you take the address and access the data memory. And the last step is writing back the result. It could come from the ALU or it could come from the memory. So that's basically, we've just put a very simple data path over here without a lot of control signals. As you can see, there are no control signals over here, but that's essentially the data path. And what is to come is this full MIPS data path. This is not even the full MIPS data path. This full should be in quotation marks because it implements only some instructions. But we will see something similar. Basically, PC, you read the instruction memory, and you read the registers after that, and some of, depending on the instruction encoding, the register that you write may be this one or this one. And then the ALU inputs come from the register file or a MUX over here, the second register, or an immediate, sign extend immediate. And then you do the ALU operation. You can use this as an address, or you could use this as something to write into the register file, as you can see. And then if you use it as an address, you get the data back over here, and then you can write that into the register file. So you have a bunch of MUXs that orchestrate the flow of the data. You have a bunch of state elements. You have a bunch of things that operate on the data. And you have this orange parts that orchestrate what to do with the data. You can see the control signals, right? They basically determine which input of this MUX is selected, what should the ALU do, as you can see, and how should the next instruction address be determined. So for example, if it's a branch, the output should come, if it's an unconditional branch, the next program counter should be set based on the result of the ALU over here, right? Which is the target address computation. And also whether the destination result, if the instruction is writing to a register, whether the result should come from memory or the output of the ALU. That MUX is controlled by a control signal that's generated by the control logic, right? These all are orchestrated based on the instruction that you're executing currently. Whether you write to the register file and whether you write to memory, read from memory, this is the memory write signal and this is the memory read signal. So all these control signals control how the data should be operated on based on the specification of the instruction that you've fetched over here. So there's no magic here. This is another single cycle processor. This is from your book, and you can read the book. It's going to be very, very similar to what I'm going to describe. So let's build this data path first. Remember this picture? Juan showed this in the last lecture. Essentially, these are R-type ALU instructions. You have 2 source registers, RS and RT, and you have 1 destination register, and you clearly have some opcodes, right? The semantics are here. You read the 2 registers, and you write the destination register and increment the PC. And this is the data path that you need. We'll start with a simple data path. You need to be able to fetch the instruction, by reading the address in the program counter. Now you have the instruction. Assume that this is only an R-type instruction for now. R-type instruction specifies that the bits 21 through 25 are the first register to read. Those are these bits, RS. The second register to read are specified by bits 20 through 16. Good. And the register to write is specified by these bits 15 through 11. So we're going to read these registers, do an ALU operation. ALU operation is specified by these 3 bits, which are generated by the control logic. And if it's an add, control logic generates an add. We will see the ALU in the next slide. And the register write signal is asserted. So the correct control signals that need to be asserted are this one and this register write. And this signal needs to be asserted, and this signal needs to be asserted based on the opcode of the add in this case. Okay? So this is the data path that you need, and these are the control signals that you need for a single cycle machine if you're doing only ALU operations, or R-type ALU operations. Make sense? Very simple, right? And ALU can be internally, it could look like this. You can study this on your own, but this is an ALU that can do multiple things, as you can see, bitwise OR, it can do in addition, bitwise and also a subtraction, as well as the bitwise AND with the not of the other argument. But it doesn't matter, you could study this on your own, there's nothing magic over here. Now let's extend the data path to also include immediate or I-type operations. How do we do that? We're going to build on what we have seen. So this is a different type of instruction, as you can see, but it's relatively similar still. This is what we're going to do. You have one source register, and the second operand comes from a sign extended immediate that comes from the bottom 16 bits of the instruction, and the destination registers are T now. The location of the destination register is kind of funny. It's not the same as this location over here. It's not bits 15 through 11, it's bits 16 through 20, right? Okay, so how do we add this to the data path that we have? Essentially, it's not going to be, okay, yeah. This is the old data path. We want an immediate, right? So this is actually the data path just for I-type instructions, if you look at this. That's actually not true. We want an immediate to be fed into the ALU. So we want to add the sign extended path, which sign extends the bottom 16 bits of the instruction to 32 bits, and we want to input that to the ALU. But if you want to execute both I-type and R-type instructions, we cannot do only that. We really need to have a mux over here. If the instruction is R-type, the mux selects this input. If the instruction is I-type, the mux selects the sign extended immediate as the input to the ALU. Right? So you need this data path element, and you need this mux to be able to execute I-type and R-type instructions together. And you need another mux over here. As I said, the destination register ID is funny. In the R-type instructions, the destination register is specified by bits 15 through 11. In the I-type instructions, it's specified by bits 20 through 16. So if it's I-type, you take this input in this mux. So basically, now we have another 2 muxes for the data path, and another control signal, as you can see over here, is I-type. Or you can think of this as 2 different control signals that are controlled in a similar way. This is what is the destination register ID? What is the ALU source? Is it coming from the register file, or is it coming from the sign extend immediate? Is the destination register ID coming from the bits 20 through 16 of the instruction, or bits 15 through 11 of the instruction? And you need to assert the register write signal. So now this is a data path that can execute both R-type and I-type ALU instructions. Very simple, right? Okay, so I'm not going to go through this, but LC3 did something similar, but we're going to see LC3 in the next lectures, and we're going to add very, very similar muxes. As you can see over here, the mux comes for an immediate instruction that is an immediate. You need to take this input of the mux. If the instruction is R-type, then it's not called R-type in LC3, but if the instruction, the second source is a register, you need to take this input from this mux, and you need to set the control signal appropriately. Okay, those are the arithmetic instructions, simple arithmetic instructions. Let's do the data path for data movement instructions. This is the load word that you've seen before. Essentially, it has a base register. It computes the address as base register plus sign extend offset. So we need to have data path elements to enable that. And you need to access memory. Ignore the translation part for now. In existing processors, you need to do translation of memory addresses, but we're not going to talk about that. But we're going to basically take memory address, effective address, and read from memory, put the result into register specified by RT. That's the specification, ISA specification. Now, how do you implement it in the data path? We're going to add memory. First of all, we need to calculate the address, right? To calculate the address, we need to access a source register, which is specified by base over here, which is bits. The ID is specified by bits 21 through 25. So that's good. We can take this, and we need to add to it the sign extend offset. Oh, we've already added that element. That's nice. We added that for I-type instructions. So we have the sign extended bottom 16 bits of the instruction, and we're going to select that as part of the ALU source. Now we can get the address. This address should be connected over here. We should not write to memory. That's a load instruction. We should read from memory. So we should set this control signal. And the destination is specified by RT, which is bits 16 through 20. So for this, we need to select whatever bits 16 through 20 are over here, which is this input. So you need to set the control signals accordingly such that you obey the specification and the encoding over here. And that's it, basically. Well, I didn't connect all of the paths over here, but you can imagine that connection. So this is the data path as well as the control signals that you need to set for load. So if you look at store, it does kind of the opposite. The calculation of the address is exactly the same. We can use the same data path components, but we're going to write to memory. We're not going to read from memory, which means that memory write signal will be 1, memory read signal will be 0. All of the control signals of the ALU will be the same as load, because we're going to calculate the address exactly the same way. Now, we're not going to write to a destination register, so reg write should be 0. I forgot to say that. In loads, reg write should be 1. You should write to the destination register. In store, you should not write to the destination register because you're storing to memory. And this doesn't matter, right? Because we're not writing to the destination register. So this control signal can be a don't care, because reg write is not enabled over here. And that's the data path and the control signals for the store word. And if you put these together, this is the entire load store data path. And I've added this is this store. If it's a store, then you enable memwrite. If it's a load, then you enable memread. So you can express these control signals with higher level abstractions, signal names that you have. For example, when you decode a score instruction, you set a bit, is this store? It's a store. And this could be directly connected to memwrite. Now you can think about how to generate the control logic also, right? Based on the decoding of the instruction. So this is the load store data path, and you can see that this is not is store. If it's not a store, the reg write is enabled. Now that's true for loads, that's true for R-type instructions, but that's not always true, right? For a jump instruction, you should not write to a register, for example. So that control logic will get more complicated as we add more instructions to be executed on the data path. Okay, so and this is the data path for non-control flow instructions, essentially. So it's very similar over here. The reason I wanted to have this different is this is load store. But if you want to execute not only load store, but also R-type instructions, you need to add a mux, which is this mux over here. Because load store, the data that's being written to the register file for a load comes from memory. But if you want to extend the data path to include the add instruction, the data to be written to the register file should really come from the ALU, right? So you need to add this mux. And that's what this mux is about. Should the data that's going to be written to the register file come from the ALU, or should it come from the output of memory? That is determined by a control signal, whether or not the instruction is a load, right? Hopefully that makes sense. So you need to add the appropriate data path elements to be able to execute all of the instructions. Okay, now let's take a look at control flows. Well, we didn't have control flow instructions. It's all sequential. PC is always incremented, as you can see over here. Every cycle, PC is incremented, and at the end of the clock cycle, PC plus 4 is latched over here. So let's have fun with the jump instruction. No, okay, this is not supposed to be this way. Okay, basically jump instruction, it's actually simple. It's unconditional. It has immediate, becomes a target address. But you need to do some operation over here. Basically, you need to calculate the target address. You need to take the top 4 bits of the incremented PC, concatenate it with the immediate, and the bottom 2 bits should be zeros because things are word aligned. Essentially, this is what it is, right? Okay, we're going to add the data path elements. So here, if you're doing a jump, you're not writing to memory, you're not writing to the register, so all those signals should be zeros, and you're not reading from memory, that should be also 0, and everything else is don't care. At least if you're considering performance, right? If you're considering power, maybe you do something in the ALU that ensures that the ALU does nothing internally, right? It doesn't waste power. So this part of the data path is kind of irrelevant, but it's not irrelevant. You should do no damage, right? You should not do something that's not specified by the jump instruction. So you should set the control signals accordingly, but we're not changing the data path over here. Over here, we need to add another path to update the PC. PC can now come from not only PC plus 4, which is in a sequential instruction. In a jump, you need to calculate the PC in a different way. And you need to take the top 4 bits of the PC, concatenate it with the 20 whatever bits over here, 26 bits coming directly from the instruction, and ensure that the bottom 2 bits are 0. And now you have a selection. If the instruction is a jump, you should select the PC update coming from this path, this data path component. If the instruction is not a jump, then you can get it from the PC plus 4 adder. Make sense? That's beautiful and very simple. We just add elements to be able to execute the instructions and the control signals as well. So what about other jumps? I'll leave this to you, but there are more complicated jumps actually in MIPS, jump register, jump and link register. So you need other stuff. Basically, for example, jump register says the value that you're going to update the PC with should come from the register that you read that's specified by some bits of the instruction. So the update of the PC should really happen with the register value, which means that you need to add this wire to the data path to be able to supply that register value to the program counter, and you need to make this mux wider. And this control signal cannot be as jump anymore. It becomes more complicated. Because, yeah, if it's a jump, you should take this. If it's a JR, jump register, you should take this input. If it's everything else, you should take this input. But everything else doesn't include JL and JLR. So if you keep adding instructions, you need to keep adding to this mux. And this mux actually becomes wider. Okay, it's beautiful, right? Everything clear? Okay, so this is actually jump and link. Jump and link is an interesting instruction. You need to write the current PC, incremented PC, to a register, in addition to jumping to a register, jumping to a memory address that's specified by a source register. So you have a source register as a destination register. So destination register should get the incremented, well, I'm not sure if it's the incremented value of the PC. Actually, it is specified as the incremented value of the PC, if I remember correctly. Jump and link register, yes, it's the incremented value of the PC. So this is actually a wrong data path connection. It's actually done specifically this way. You should really save the PC to a destination register in jump and link, but the PC should really come from here. So you should be very careful when you're obeying the specification of the ISA, right? You should do the right connections in your data path, and of course you should set your control signals correctly to execute the instructions in a way that is expected by the programmer, which is the ISA. So this is for your information. These are different jumps in MIPS. There's also a MIPS cheat sheet that we've uploaded on the course website that you can look at that actually summarizes all of the instructions in MIPS. Okay, we have conditional branch instructions. Let's take a look at how that is executed. As you can see over here, so there's a branch delay slot in MIPS, which we're not going to talk about, we're going to ignore for now. It's actually an interesting design choice that was made in the ISA, which is not considering future generations as much, but that's okay. So let's execute this branch instruction. So branch instruction, basically, this is a BEQ, branch if equal instruction. You calculate the target address this way, PC plus sign extended immediate multiplied by 4. And if the source and destination registers are equal, then you take the target address, put it into the PC. Otherwise, you take the next sequential program counter and put it into the PC. So you basically need the mechanism to calculate the target address. Okay, wait a second. So that's PC plus sign extend immediate times 4. And it's coming from somewhere over here. I cannot find it over here, but you need to finish this data path. Okay, but I think what I would like to, oh yeah, it's over here basically. This is the PC plus sign extend immediate, that's the branch target. So you need to put this new thing over here, new adder. So we add a new adder to calculate the target address because we actually need this adder to calculate the branch condition, right? This adder subtracts the source register from the destination register and figures out whether the branch should be taken or not taken. So you have control logic for the branch that says whether you should take this, which is the target address, or you should take the program counter plus 4. Okay? So you need two, well, this is an adder. This doesn't have to be a complete ALU, but you need one adder inside the ALU and you need one adder over here. One is used for doing branch condition calculation as specified by this. If these are equal, then you take the target. And the other is used for doing the target, branch target computation, right? So now you need two adders. That's how the data path becomes bigger and bigger, because you need another adder to be able to do this. Okay, and you can study this on your own. So putting it all together, this is what you get actually. This doesn't include all of the instructions. There's more, JL, JR, JLR, we discussed briefly. We don't have them, but we're going to get there. Okay, so I think this is where we will stop. We'll talk about the single cycle control logic, not next week, but the week after that. Have a nice Easter break, and I'll see you in a couple of weeks.